so then we're ready for part G. So what would your answer be for part G?
50 joules.
Seems like a good approach. Okay, so you saw that this was a conservation of energy problem. Of course, there was a big clue because they used the word energy. So once we've let go of the rope, the object is going to swing down like this. So you said that the total initial energy will equal the total final energy. That's good. Now, one thing you have to check is to make sure that energy will really be conserved. Because I noticed there's some problems your instructor gave you when energy was not conserved. Well, how do we know that energy is conserved here? We have to focus on who's doing work on this object. Well, what are the forces on this object? Well, there's the weight and the hinge force. Do you remember whether weight is a conservative force or a non-conservative force? That's the force of gravity. Is that a conservative or a non-conservative force?
I'm not sure.
So the force of gravity is a conservative force, which means that it doesn't change the mechanical energy. We kind of take that for granted because we're always using conservation of energy for bodies that are falling due to weight. So gravity is conservative. We should memorize the conservative forces this semester. They are gravity and the spring force. I think those are the only forces you've seen this semester that are conservative. So mechanical energy is conserved if the only forces are gravity and the spring force. Those are the only conservative forces you've seen this term. Pretty much everything else you've seen this term is non-conservative. Now, the hinge force is non-conservative, but it's still not doing any work because it's not moving anything. The hinge isn't moving. The basic equation is that the work by the non-conservative forces is what changes the mechanical energy. Well, gravity is conservative, so that doesn't appear here. And the hinges are not conservative, but they're not doing any work because they're not moving anything. So you were correct to say that the mechanical energy was not changing, so we can use this equation. But again, I have seen some problems in the sample exams where energy was not conserved, so you do have to check for that. For example, if friction was doing work on something, then energy would not be conserved, and we can't use this approach. Now, the kinetic energy here really has two parts, rotational and translational. But the problem was only asking for the total kinetic energy. So I'm not even gonna bother breaking that into two different parts. I'm just gonna say this is the total kinetic energy and not worry about the parts because the problem was treating the two parts as a single type of energy.
But initially there, okay, yeah. I was gonna say that initially there would only be translational kinetic energy, but that, there wouldn't be any.
Yeah, originally there was no energy at all, neither rotational nor translational. At the end, there will be both, but we don't need to figure out how much is translational and how much is rotational, because the question didn't ask. Now, we know that originally, as you just said, there's no kinetic energy because we start from rest. Since we're starting from rest, we start with no movement. And now, why is this final potential energy going to be 0? Well, you said that the initial potential energy here was L over 2 mg, is that what you used?
Yeah.
How did you get that?
Because the center of mass is L over 2 height above, like, I just thought about where the center of mass starts and where it ends.
That's really a really good way to think about it.
It seemed like since it ends at 0, then.
Yeah, that's a really good way to think about it. Now again, different parts of this object are moving different amounts. So it's not really clear. So different parts are going to lose different amounts of potential energy. But again, we can use the trick of just pretending that all the mass is at the center of mass. We can use the trick of pretending that all the mass is at the center of mass. So I should have made my two pictures at the same level. But anyway, so we're going from here. Well, where's the center of mass going to? Here. The center of mass is going from this height to this height. And then basically use the trick that you can choose whatever you want to be the 0 point for energy. The most convenient thing was to say that this was the 0 point for energy. And then the height that we need is just the height from here. Well, you're right that the height above the 0 point is L over 2. That was good. And again, then, since we chose this to be the 0 point, the final potential energy is 0. And your answer, so we have L over 2, that's 1/2, and the mass was 10 times 10. So we got the final kinetic energy was 50 joules? Is that the answer you got?
Yeah.
All right, you didn't seem too happy about that. Was there anything that was making you worried about that?
Well, I wasn't really sure if I was just completely off about how I was thinking about the problem.
All right, well, now you can be more sure. Yeah, it turned out that you were thinking about this exactly right. We treat the whole thing as if it's concentrated at the center of mass, and we might as well choose this to be the 0 point for energy, since that's the lowest point the center of mass gets to. So then the initial height would be L over 2. So that was a good way to think about it. Okay, so the part that's most important to keep doing here would be parts E and F, where you had to use this equation and you had to put in the signs yourself. And again, when you have an extended object and different parts have different accelerations, you focus on the acceleration of the center of mass for Newton's second law for translation. All right, so should we try the other torque problem?
Yeah.
Okay.